So, welcome everyone to the Berlin-Tokyo Viral Cloud. This is edition number 9. And we're very happy here to have Professor Walter Ruggieri Waldman, who is a professor at the Universidade Federal de São Carlos, in Brazil. And he's been in Berlin for since the beginning of the year on a Humboldt fellowship at the Plant Ecologies department of the Institute of Biology in the Free University, where we also have some members here who are in that same department, James in India. And yeah, so he's going to talk today about microplastics. His research is in microplastics and soil biota, and working together with soil ecologists, and his expertise is also in polymer chemistry. So this is also something interesting for us in Berlin, because we've had a project. A lot of the people here today are in our DIY Hack the Panke group, which is about an urban river in Berlin. And the first project, and really the one that we've spent a lot of time dealing with, is microplastics in the Panke River. So Nana, who's here, has been a main person in that project, as well as Kat Austin, who isn't here today. So we're very happy to have Walter here, and yeah. So.
And thank you for the invitation. Thank you, India, for make this happen, make the contact so I could meet Christian. Okay, so my topic is polymer degradation. Currently, I'm working with microplastics, and I am going to show you some interfaces between polymer degradation, art conservation, and art production, and also some results from microplastics we have here, and some fundamentals about polymer, so we can understand polymer degradation, then their role in art. So, can I? Okay. No? Okay. So, just a very funny introduction. Polymers are really long chains. If you want to have some notion about the size, Barilla number 5, we use this numbers, the length divided by the diameter, so we can know how long some fragment or some piece of particle is. So this is the property that differentiates a fragment from a fiber. So we have 200 and a bit more diameters in the length of spaghetti. In the regular polyethylene, you have 10 times more. So it's more or less, if you have 10 spaghettis in a row, you have the size of a polymer if they had that diameter of the spaghetti. But polymers are not straight, so they always entangle into themselves, and it's more similar to this spaghetti, just separated from the water. Polymers move, so we need to know that polymers are dynamic. They have some limit. They do not have complete freedom of movement. So each part of the polymer must respect the other bonded to this part. So each monomer has some freedom of movement, but not the entire polymer. And because of that, we have this kind of stuff we call free volume. This is important to know about the toxicity of polymers. I know I visit the art laboratory, so I see some installations about toxicity of the polymers, hormones, and this is the mechanism. They move through the polymers. So it's important to understand. Then we can understand that the free volumes should be the empty spaces between these spaghettis, between the polymeric chains. So we have chemicals inside the polymers. There is no way we have polymers in our daily lives to not have chemicals inside. We have that, but in industry or in the laboratory, in our daily lives, we need chemicals inside the plastics in order to have the properties we want. So we have several additives. It should be like the sauce for the spaghetti. So the sauce is the most fit example for the plasticizers. And plasticizers are very common additive used when we research the toxicity of plastics in general, like the PVC. PVC is the kind of plastic which receives a lot of plasticizers, and plasticizers has the function of increase the free volume and make the polymer be more flexible. So this tomato sauce is a perfect plasticizer for spaghetti, and it would be no problem if we had no toxicity, but we have toxicity for almost all the chemicals inside, all the additives we use in plastics. And also, one important stuff to understand polymer degradation, microplastics, and what's going to happen with art as a function of the time is the crystallization. People usually don't know that polymers can crystallize. If you have crystals, always you have brittleness. So as a function of the time, we can delay that, but we cannot avoid that. As a function of the time, polymers, if the polymer is crystallizable, it's going to crystallize. Somehow, eventually, it's going to crystallize. When they crystallize, they are becoming brittle. They can produce microplastics. They can produce crackings and break the piece of art. This is a paper I published with Matthias in my beginning here. It's about degradation and plastics. So this is kind of graphical representation what we have. So when we have plastics exposed to the weather, but not just weather, that's the problem with the art. If you conserve your art in an art gallery or a museum, you'll have the time. Even if you control the light, the oxygen, other parameters, you are going to have your plastic piece eventually breaking because we have the effect of the time. So in this paper, we talked about weathering, which is basically thermodynamics when we insert energy into the system. But even if we take care of that and we don't insert energy into the system, we have the time. So it's the kinetics. So time is key, and it's going to degrade the polymer. So it's the key problem of art conservation. So also we break chains, we make polymer brittle, and we make them opaque very often. So this is the brittleness. It's the part that makes the microplastics, because you have mechanical stimuli, and then you are going to break in small fragments. We have also wettability. I think this is a very interesting property to talk to artists, because also we can have wettability being worked if we want to make it part of the art, of the piece of art, because we can change the properties of the surface and it can affect the interaction with paint or other materials. So this is one example of disposable polystyrene glass before degradation at the left and after degradation at the right. So you can see the water almost do not interact with the surface at the left, but on the right, it's interacting very well. So we call it wettability, and the surface at the right, it's much more wettable for polar solvents as water than when they are not degraded. So it plays a fundamental role when it interacts with the environment, of course. This is one film I did for a presentation. It's just the middle of this plastic piece was protected with a piece of paper in the format of a heart. and then I put some water. The water goes just where it's degraded, the rest of the Petri dish. So you can see the water here. So when you have some installations in science museums, you can have this kind of dynamics presentation. So you are not seeing the modification on the surface, but when you have the interaction with the person, with people, then they can put some water or some other stuff on the surface, and then it's going to interact differently according to the region of the piece. So it's an interesting property, and also brittleness. So this is a very old plastic chair. This is one student trying to break the, sorry, I lost the control. So here we have a box exposed to the, a box, it was in the garden for years, but partially exposed to the sun. So the back part of the box, it was not exposed to the sun. This is the piece not exposed to the sun. And now this is the piece exposed to the sun. So you can break easily. And when you have breaking, always you have this kind of phenomena. You break two pieces into at least two larger pieces, but also smaller pieces. And when we get closer to the stove, I did this at home, you can see the smaller particles. And then when we approach the smaller particles, you can see evidence of even smaller particles. So it's a process that, remember, that the origin of the word atom, the Demosthenes, I don't remember the name of the Greek philosopher, which said that you can break things infinitely or until you find the atom. So two lines of thinking. So we can have that. So if you break something into two larger pieces, you are going to have several smaller pieces of particles. And this is the fundamental of microplastics formation. Okay, sorry. About microplastics, we have controversy about microplastics. Let me give them a short abstract of this controversy. People are always talking about microplastics, and it's here in an ecology group, it's very easy to understand that microplastics is a problem. Plastic pollution is a problem. But when we try to have an interaction with the society, we have some strong answers, maybe not believing the same. And we have the discussion, okay, microplastic is bad for the environment or not? First of all, we have one definition, two definitions I would like to share. So contamination and pollution. Contamination is something that shouldn't be where it is. Pollution is that contamination when you can establish a relationship between the presence of that contamination and some harm to the place where it is. So we know for a fact, it's no problem with that, it's a consensus. We have microplastics everywhere as a contaminant. The problem is it a contaminant or a pollution, a polluter? And that's the problem. We need to talk about that in the science universe. So it's not established yet how harmful microplastics are in the environment. We know they are harmful in the laboratory experiments, but the problem is taking the plastic pollution to this kind of context, if it's harmful or not. the first debate should be if the microplastic should be there or not, because even if it's not harmful, and it is harmful, we know that. We don't know how harmful it is, but it shouldn't be there anyway. So it's a kind of transposition of the discussion going to the how harmful it is or not. Well, regarding that, this paper tried to make some assumptions and tried to provide some fundamentals for this kind of debate. So they did this graphic of relation between concentration and how harmful they are. So in the green curve, we have the concentration where they are found in several environments. So it's a very general graphic. And in red, they took some species common used to assess the toxicity and check the concentration where where you have harm to this species, like reproduction, growth, or mortality. So they showed that we have some orders of magnitude between the concentration in the real life and the concentration where they are pretty heavily harmed by the microplastics. So this is one of the fundamentals of the discussion. But this is part of the debate, right? So this is part of the debate that, okay, they are not so harmful as we think they are. Other part of the debate is showing the limitations of this information. So when you see this concentration in red, you need to consider that we are not going to produce less plastics in the next decade. So with the harm the environmental movement is doing to the petrochemical industry, it's a strategy stated in all the media you want by the petrochemical industry to drive their efforts to the polymer side of the petrochemical industry. Well, not even with the COVID is expected a decreasing of the production regarding the previous year. It's expected decreasing of the expected production before COVID, but we are going to have more production than this year. It's not expected in the next decade we have something like a curve is going down. It's not expected. We are not going to have suddenly now more a better management of the waste residues in the world. So we are going to expect the same kind of input into the oceans, into the soil, into the air regarding microplastics. So we are seeing this green curve shifting to the right, nonstop, continuously. We have no evidence of this shifting being slowed down. Regarding the red curve, which relates to the harm, the most of the experiments is performed, and we are doing a review right now showing that in the laboratories, they are doing the experiments with pristine polymers. So the polymers didn't pass through degradation, and the most of the experiments didn't receive any additives. They are performed with microplastics made for this kind of experiments. So you can buy these nanoparticles or microparticles very clean. They come to your laboratory, sterilized, round. One of the sources of the toxicity of microplastics is their edges, so they can cause inner damage to animals. So this consideration of the harmness, how harmed they are to this species, it's conservative because they consider have harm, and we need to consider also when you have a mild harm, because in the environment, species are not exposed just to microplastics, but to several stresses. So it's one of them. So if it's mild, it's a stress. So you need to consider also the mild stress because we have a multi-factor stressing to the living species. You need to consider that these microplastics is sterilized. If you are assessing ecotoxicity, it's expected to have this experiment reproducible. So people sometimes, researchers sometimes concern too much about reproducibility to allow someone to have the same results, and they forget to get close to the real situation, which is the presence of the chemicals inside the plastics. And one other thing I didn't tell you, the sorption of the current pollutants into the environment, because microplastics can stick these pollutants into on its surface. So we have these considerations to make the red curve shift to the left. So what we are seeing right now, if these curves are right, we are going to see these two curves overlap sometime in the future. We don't know. So the question is if we are waiting the non-return points and other kinds of problem. Sometimes people, we can debate about that later, but it's complicated when you need to argue, or when you need to discuss science, ecological science with the productive sector. So we have these discussions, and we need to take into consideration two kinds of questions. Sometimes people ask for us to prove that the pollutant it's harmful. And sometimes you need to change the question. You need to put this question to the production sector. Where is the evidence that this product is safe? So now, right now, people are debating that the environmental researchers shouldn't find the motive of the ecotoxicity. Our work is find the ecotoxicity. Who must say which kind of chemical is toxic or not is the producer, who is not obligated to say what's inside the polymer. Okay, the regulation doesn't go too far, this far. Okay, so about impact is that. About fate, we now are looking for microplastics everywhere. This week we had microplastics in the highest mountain in the world. It's the news of this week. And we have these two papers, recent papers, talking about that. So first, we have 1,000 tons per year falling in South and Central Western US protected areas. This paper on the left, they calculated that as microplastics, and not just raining, but also falling out without the rain. Okay, but it's kind of plastic rain. But they have the results for rain, microplastics falling along with the droplets of water, and microplastics falling all the time. And also in the right, we have a kind of debate also. It looks like kind of fake news. But in the oceans, we don't find all the plastics that we should find floating in the ocean. We have a huge gap. So since we didn't find these plastics, because we know the input and we know more or less how much is there, so we have some orders of magnitude of gap. And some people are saying, okay, look, they are going somewhere. It's not bad. So they are biodegradable. Oh, look, we don't need to concern about that. And so we need to find this gap so we can add to this discussion. So we don't have this kind of weird conclusions about this gap. And this paper found a very good point for the fate of the microplastic, which is about going to the sediments in the from the rivers. So we know we have tons of microfibers, fibers being released in our washing. Yesterday, we are having now a conference about microplastics, and yesterday they showed an experiment showing that we release microfibers not only washing, but walking by. When we move, we are also releasing microfibers. They did a very funny experiment with that. I can find you the data, I took note. But we have also this kind of release. So with the water, these microfibers might go to the soil or to the water treatment station, or simply go to the river. And into the river, they go to the sea, and in the sea, they can keep the sediments and the particulates in the river keep having an influence in the sediment. And I didn't know that. I found it very interesting. They have an influence in the movement of the sediments under the sea, under the ocean, under the water. And they simulated that, and they found a lot of microfibers in the sediment. They found the highest concentration of microfibers in the world. Until now, I am going to show some results for you about that, but in the sediments of the ocean. And they simulated these movements here in this experiment, and they could prove that. So we have a lot of microfibers going to the sediment in the bottom of the ocean, the floor of the ocean. And this is not safe because we have all the invertebrates there feeding with their stuff in the sediments and also with microfibers, and it's going to us. If not the microfibers, but at least the chemicals inside the microfibers might be part of the trophic chain until us. And if it's not going until us, it's going somewhere. So it's not because it's not harming us, it's not harming the environment. So we need to think about that. Okay, so the problem of the microplastics started with the macroplastics, which was a register in the 70s, but it was not a big deal at that time. And today, microplastics is a hype subject, and it's because of many people say that it's because of this garbage patch in the Pacific. So we have this kind of concentration of the plastics that floats in the Pacific because of the gyres. This is the main gyre between the west coast of America, North America, and Asia. And this kind of macroplastics, it's not an island, okay? It's just floating. We call it an island, but nobody can walk there, but it's huge. And it dips, you can see 5 meters under the water, but you cannot see too much above the water because of that accumulated so long without notice from us. But now we can see, and it's huge. And there we have the macroplastics and the microplastics. This is just to show you that microplastics usually is defined as being less than 5 millimeters. But there is a lot of definitions according to what you are looking for. But I think that microplastic, the first time microplastics was used to talk about pollution, it was about a very small particle. So it's micro-like, micro management, or micro as a prefix for a microcomputer. It's not related to the size, but because it's small. So when you have small plastics, you can use microplastics, but in science, we usually link that definition to some measurable dimension. Well, we can divide microplastics into primary and secondary microplastics. Primary are the microplastics done in that size for the product. And just to have some examples, this is from a recent report from the intentionally added microplastics in products. So it's the amount of microplastics added in products just in Europe. So personal care, like exfoliating cosmetics, soap, so you can rub your face and get rid of the dead cells. Around 1,000 tons, a bit more, almost 2,000 tons in personal care. Paints and coatings have a lot of microplastics. I am going to talk heavily about paints soon. Industrial abrasives, it's like exfoliating, but industrially, it's to get rid of rust or other dirty on surfaces. So sometimes you use sand when you get rid of dust of rust from metals, but when you have something that cannot be harmed by the sand, you use plastics. So it's a mild abrasive. It's 1,000 to 5,000. Agriculture, we have 8,000 tons of plastics a year in Europe. And oil gas confirmed they use, but they refused to give the numbers to the report. All these numbers were given by the industry. They were not measured. Here at the right, just so you can have a notion about the sources. Personal care, which is very, it's a lot in the media. It's 2% of microplastics ending up in the oceans come from the personal care. So this is also part of the debate. Sometimes we dedicate a lot of efforts, valid efforts, to tackle some pollution sources, but sometimes we are not strategically doing that because it's just 2%, and we have tires, it's almost 30%. Microfibers, 35%. And my favorite topic, it's the thing we call city dust, which almost one-fourth is 24% of the microplastics go into the ocean. City dust is a category of several different pollutants in the cities, in the urban spaces. And that's my favorite because it's overlooked. So we are looking for, and I am going to show you some really fresh results about what we are doing here. Okay, so secondary microplastics. This is specifically the point that made me ask India, because I knew India was very interested and engaged with art. I approached India to ask for talk about art, but not, well, I am not an artist, but I think this is a thing, it surrounds us and we don't take attention. And I think it could be subject for some installation, some action about that. So when we talk about secondary microplastics, it's about the microplastics made from the degradation of the plastics. It happens in the environment. So a PET bottle goes to the environment and then it's exposed to the weather and then it breaks. But it happens in the cities. So you have the graffiti here. You have this rubber in the left down, in the left bottom part of the slide. And my favorite is the paint here in this, I don't know how to say this word in English, but you are seeing. So you can see that with the weather, you can have the degradation, and with the mechanical stimuli, or simply because it's not sticking anymore and it's brittle, it can fall and you don't know where it is. One of the works we have is finding this kind of microplastics, but I think it's easier if you go and see that the plastic is not there anymore. If it's not there anymore, it's in somewhere where it shouldn't be. So that's the point. So secondary microplastics is everywhere. this is the process we do just as a curiosity. We do to find them. So we have density. Usually they are less dense than the most part of the soil. So you use a solution. We use here sodium bromide, but you can use even sugar, even syrup. And then they float with organic matter. Then we digest this organic matter. So we use a reaction in order to make this organic matter vanish. So we have just microplastics, then we go to the microscope, and then we go to see the microplastics. And then we go to an analytical equipment to say which plastics there. Without spectroscopy, which is the struggling part, you can say you have a lot of plastics, but not which kind of plastic they are. Okay, let me show. James and India are going to see this tomorrow with more details, but this is some microplastics coming from a graffiti wall here in Berlin. So here you can see in the soil, I'm going to say some details later. Here you can see the several layers of graffiti. It's a wall where you can graffiti legally, so you can graffiti on the top of other graffitis. It's allowed, so you can go. It's ephemeral. You are not going to have your graffiti forever because everybody can graffiti there. So we went there. It's a hotspot. So the idea was to try a new method for separation, which worked partially. And then we had these results, which was stunning. Stunning for the research, not for the environment. For the environment, it's bad. So here we have the examples of these fragments from abrasion and these spherical colored particles, which comes from the spray. When you spray some surface, when you want to paint or coat some surface with the spray, you have part of the spray that hits the surface and stick there, part of the spray that might go to the surface, but in the turbulence close to the surface, it can goes away. Or also it's a spray. So you have a cone, you have a distribution. So some of them are not going to hit the surface, never. So then they go to the air. The solvent evaporates. They form these spherical particles, and then they fall out. And we found a lot of abrasion, a lot of fallouts from aerosol. We have found a lot of plastic agglomerates. It's an intersection of microplastic field with the geology. So they are some people are arguing that we are going to have some composites of plastics, not necessarily microplastics, of plastics with other structures. So when you have some fire, and plastics in the place, you can have the melting of the polymer, which is not burning, and the formation of a composites with sand, with wood, with other structures, and it can stay longer. And there are several kinds of plastic agglomerates. It's a field apart in the microplastics field, and we found some. So we have this charcoal here at the right with some aerosols. It's the picture in the microscope. It's not good because we had so much microplastics. We couldn't find a plane to have a focus on the microscope. So we have other charcoals with several aerosols, but this one has this red one. But now I am seeing I could choose another better because there are some with the spherical inside these risks, inside the rigs. So it's almost a plastic agglomerate. And this is, it looks like an abrasive part produced from abrasion, which burned in that place. We found a lot of charcoal there, a lot of coal. So it's probably product of that. This is one of the pictures we can see in the microscope. Usually in this kind of magnification, if we are lucky, we find one or two fragments. Just to give you a notion of the magnitude of these plastics there in the top 5 centimeters in the region. So it's big, and we are going to work with that. This is the highest magnification we have, just so you can have a notion. You can see the largest here in the lowest magnification. And here you can see in the highest magnification we have, you almost do not see. This is a magnification of the previous picture. You almost can't see the smaller one, which you are not going to have a notion about that in this larger magnification. So our problem now is to separate well this dark matter. We don't know what's it. It shouldn't be here, but it's a thing we are going to solve here in the laboratory. But we have a lot of microplastics that could be under this dark matter. So you can imagine maybe we have other order of magnitude of concentration of plastics regarding the spray painting using spray. This is not a problem of the graffiti. Of course, graffiti has an impact. Of course, we could do better doing graffiti. We have contact with a graffiti artist here in Berlin. We are trying to see if we are going to see if we are going to try, it's a conversation, to develop new methods so graffiti could be more sustainable or could not spread too much microplastics. But we have several considerations in that regard. First, this is super concentrated. This picture here show a concentration you can't find when we work with monitoring. You can't work with that. We need to dilute these results are going to be diluted in order to count. We cannot count that. So it's too much. And someone could say, okay, so it's a disaster. It's not, because it's a very specific situation. We knew this could be a hotspot, so we went there to test a method. So it's like we need to go where we know where there is a lot of microplastics, so we can test a method. But then we found the thing we never expected to find. But we have a condition there. This kind of microplastic, we don't know that yet for sure, but we are suspicious that this is not a very mobile microplastic. So it's the condition you must have. If you have a continuous input and not mobility, it's a condition so you can have a hotspot. Having a hotspot, it's not a good thing, but it's not so bad as the microplastics that travels kilometers, hundreds of kilometers, pass through several processes to end up in the bottom of the ocean. Of course, we are more concentrated than the highest concentration of sediments, of microplastics in the sediments in the ocean. But of course, it's not fair, the comparison. So it's not so bad like this, but we can have this kind of situation. We have the graffiti wall as a proxy of other kinds of processes that we industrially do a lot in indoor, but also outdoor environments like these ones. So all of these situations use spray painting in the industrial world. Of course, you are surrounded right now by several objects that were painted. using spray coating process. And we have these two also. I would like to emphasize the polyurea coating technology, which is new for aeolic energy. This is very used now, fire retardant coatings for wood because of the fires we are increasing in the world. And the most ironic application, anti-graffiti paints and coatings, which is ironic because we discovered that using graffiti. Okay, and this is just for you have the notion. I don't know how to edit videos very well, so I couldn't emphasize the situation, but I think you can see when this guy is going up, painting again this part of the ship, you are going to see clouds of red paint going from the painting. So all these clouds are going to be microparticles. Look at that. Are going to be microplastics, likely to end up in the environment if they do not control very well. And I think it's impossible to control very well this kind of pollution. Okay, regarding microplastics, that regarding polymer degradation and conservation of art, I would like to show these two artists here. The first is Vibeke Pandikov. It's a German artist in Finland. She does this kind of works. I am going to show an accelerated. The point is not to show the technique. I know you don't know to learn about that, but how the processing of the material can influence the conservation of the art later. So this artist works with plastic bags. It's a very smart process. I love it, this processing. So she used temperature, which can affect the stability of the plastic later. Then she used several textures, and then she works, this is the part of the work she tries to emulate leaves. And you can see when she goes to the part of the texture, first, she's using heat all the time. But now she's doing the texture for each leaf of his work, of her work. And this part is the part where she's affecting selectively the potential of degradation of each part. So when you use heat, if you are not using well in a controlled manner, you can affect the degradation. And if you don't affect the degradation, you affect the crystallinity. Where you have more opaque regions, so this picture here at the left is magnified at the right, and you can see the details. So when there are some bubbles. These bubbles show that the thermal input was too much. So this is a degraded part already. When you have opaque parts, could be crystallization. Crystals, if they are not degraded, crystals are more resistant to degradation than the amorphous part. So this piece of art is going to have two different kinetics, two different speeds for degradation. So part of the leaves are going to degrade before than other parts. So it's one problem that conservators of art find in their job. Also, this artist, Mibongeni Buthelezi, don't know if I did right, from Johannesburg. He has this very creative work. So he used like hair dryer, but industrial dryer, to melt partially the plastics and do their compositions, his compositions. So you can see he collect his plastics in the trash, and then he used them to make his pieces of art. So one of the problems regarding conservation later is that he used trash, which is part of his art. It's part of his concept. But later, it's going to harm the piece of art if it's not his proposal to be ephemeral. If it's his proposal to be ephemeral, it's no problem. It's part of the concept. It's part of the piece. But if the piece it's meant to be preserved later, it's not a good choice because it should be to work when the plastic is in the trash. The degradation process could be started, already started. And some parts, if it's so heterogeneous like that, and it's the pieces meant to be preserved, it's not a good choice. So it could be, if you have more degraded pieces, this part is going to fall off or peel off before the other parts. And this is one thing I would like to tell you, because maybe someone would like to have this approach of having the piece of art being degraded in front of the eyes of the society in a short time scale, not in a day, but maybe in weeks. There is this kind of polymer, this kind of additive. It's called oxo-degradable. This kind of additive it's matter of environmental concern. So when you go to the market and you buy a plastic bag in your city, it's a new law saying that you cannot use conventional plastic bags anymore. If the supermarket doesn't charge you more because of the plastic bag, because biodegradable plastic bags are expensive, so it must be charged. They are not going to not charge you. If they do not charge you, it's probably they are using oxo-degradable plastic bags. So what's an oxo-degradable plastic bag? It's a conventional polymer, polyethylene, low-density polyethylene, with a photosensitizer. It's usually a fat acid reacted with a heavy metal, a potentially toxic metal. It's not used the term heavy metal anymore. And these metals can be toxic. They are likely to be toxic. They are good for the industry because you don't need to change the process. The industry, if the industry could process biodegradables the same way they process conventional polymers, we would be in another stage of use of biodegradable. The problem is that to process biodegradable polymers, we have less margin for errors. They are much more sensitive to heat. So the processing is more expensive. It's not the higher cost of the biodegradables, it's not just because of the cost of the raw material, it's because of the processing also. And they need to change everything to adhere to the biodegradable polymers. With the oxo-degradable, no, you just don't. You just add another additive, and then the plastic exposed to the weather is going to fragment easily, fastly, and you're not going to see anymore the plastic. Which does not mean that they are not going to be there. They are going to be there as microplastics, and we know that. So just as an information, here in the laboratory, in 10 days, using 95 degrees, I can transform a plastic bag in nothing. They keep being a plastic bag, but I can't hold the plastic bag anymore without breaking it. If you keep it 10 days in this temperature in an oven, you are not able to take them anymore. You need to get something and remove the plastic from there. So you can fabricate, you can use less time, and this polymer is going to break in the installation, in the art gallery, if it's the purpose of the artist. But also, just to not tell that, European Union tried to ban that. It was in the way, but because of the coronavirus, now it's a step back. There is this report showing the problems and the inconclusive knowledge about the oxodegradables. Part of my work here is working with oxodegradables. We have an experiment to be started soon, but now it's not going to be banned anymore because of the coronavirus, the new situation. So it's a struggle. It's a discussion we are having now in the society about oxodegradables. But I think oxodegradables could be a tool for artists if they want to use this kind of ephemerity in their pieces. And also the thermal processing could be something that could be worked in a longer time scale for a piece of art. Just to talk about degradation. And shortly, I am out of time. These are some pieces from museums and art galleries that are facing these kind of problems now. In New Zealand, these kind of pieces you are seeing are usually made from natural materials, but now because of the contemporary times, just because of that, people decided to use plastic instead of natural materials, and now these objects must be preserved and they are facing problems because of the reason I have just told you. They used plastics close to the time of the degradation, time of the microscopic signs of degradation, and they are breaking apart in the museum and they should be preserved. This just this slide just to show you that degradation is a thing that should be controlled and fought in the museums, but also there is this line of thinking that we should embrace degradation because plastic, it's last week we had the conference here in Berlin, but online, called Plastics Imperial. And when we have a lot of problems preserving pieces in museums and art galleries. And one of the main strategies is cold temperature. And there is this discussion about if we need to preserve pieces because we are spending too much energy to preserve the species, to have them preserved instead of 20 years, we are going to preserve them 50 years. So there are people suggesting that maybe we shouldn't preserve the pieces too much. It's their decay is part of the life of this material. So it's one of ways of thinking regarding art and polymer degradation. And there is this work, this beautiful work about curated decay. So it's not just plastic, but about decay in art and in life. This is one example about a museum in England. It's about the George Best boots. James, I don't know if I don't remember the name of the museum, but James knows George Best, right? Yeah. So it's the work of preservation. You can see at the left the way the boots were when they receive it and the work of conservation. The work of conservation is almost the same conservation of plastics. It's practically the same that the conservation of art in general. So you must rebuild the piece, but you should show that this piece was rebuilt. So the people are not being conned, are not being they know the piece they are seeing is representative of the previous piece, but not exactly the piece. And this is a very interesting case of conservation. Did you see? Someone saw that, James? I'm not seeing the face of everybody, but this piece of art was outdoor piece of art saved several lives recently. And now they are discussing about the preservation of this piece of art. They are seeing if they are deciding if they are going to return the piece to the previous form, or if they are keeping the marks of this remarkable event in the piece of art, because this is part of the piece of art, because this art was outdoor, interacting with the weather, and maybe the train is part of the weather. So it's a thing people could think about. Just a fast about conservation. It's a thing I love. It's plasma treatment. You can treat surfaces of pieces to preserve them against the environment, but also you can change the wettability of objects using plasma. So you can make things more wettable or less wettable. If you have some, and it's not expensive, it's easy to do. I had a dinner other day, and I don't know how to say in English, but this tissue we put on the table, and then the plates and food, etc. And we call towel in Portuguese. So this towel, you could not wet this towel. So you put the water, and it was a bubble, spherical water, and you just move the water on the surface. So I saw some people working with this changing. You can do a gradient of change of surface, wettability on surface. So you can have, for instance, parts of a screen, parts of a surface, wettable by organic solvents, and part of the surface wettable by polar solvent. Then you could use paint, water-based paints and solvent-based paints to paint differently the same surface, having different reactions of the surface to the action of the paint. So I think it's also a technology that could be used by artists. And the last artist of this presentation, it's not related to polymer degradation, but to waste pollution. It's Max Liberon, and I love this. This lady is awesome. She is a professor of the Memorial University. She's an artist also. She has some installations working interactively about capitalism, about waste, about trading. And she runs this civic laboratory of environmental action research called CLEAR. And she has a book being released now next year, Pollution is Capital, Colonialism, sorry, by the Duke University Press. So I recommend you going after this artist researcher because she's awesome. That's it.
Thank you very much.
Oh,
Walter.
my pleasure.
That was a very interesting, precise chemical, but also interdisciplinary journey you took us.
I tried. I'm sorry if I couldn't.
And I think we all have questions and ideas. And now here we're in the grid of 9 people. Some people had to leave, but thank you for your contribution.
I think India just left a little message before she had to leave or something, and she said to think about the Panka River, where the big graffiti space is actually along the waterfront. So actually on a wall where the river is below it, that all the particles that fall down fall into the river basically and get carried down further.
Yeah, I it's a pity we couldn't make the walking, right?
Yeah.
Because we tried, but now.
Mm-hmm. Well, let's discuss. I mean, I have quite a lot of questions, but probably also everyone else. I'm really intrigued. We hear a very interdisciplinary group: scientists, artists, theoreticians. Who wants to start? Questions, objections?
I am just taking off my coat. Just 1 second.
If I can start, because I have written the question in our chat, but maybe it's better to ask it loudly. because I was thinking about this connecting of artistic practice and preserving at the same time. And the topic of preservation of contemporary art is like a really old topic, let's say already. And we know that we have a lot of ephemeral forms of art. So it's challenging to preserve them, what is also a contradiction because from the scratch, they should be ephemeral, but to put them in the context of history of art is like, it's a trial of doing that. So I was thinking about what we have right now, like our discs, our computers, our CD plates. First of all, what to do to preserve them, like to be able to get the information after some time, because we know that after longer period of time, they are not so easy to work with them. And the second question is actually about this including of the process of preserving in art production, because your presentation inspired me to ask this question, especially this painting with plastic. Maybe we could think about let's say post-life of our ephemeral art imprinted in this, plastic elements as a continuation of the performative process, this ephemeral art. So this is actually one question and one comment. So the question is actually what we can do with them in order to keep them alive for longer.
Yeah, the first part of the question, how to preserve, there are several technologies and there are several complications to apply this technology. The most used technology is cold storage. And according to the plastic, and this is key in the preservation, they need to identify the polymer. Because if, for instance, a very big problem is the films made for cinema made from nitrate cellulose. So if you have nitrate cellulose or nitrate cellulose or acetate cellulose, you need to change the air. So the atmosphere must be renewed to not accumulate the acids being released. But if you have PVC, you need not to change the air. You need to preserve the air. We need to lock them in a place because the plasticizers, when you renew the air, the plasticizers are being removed, and it's remove the plasticizer from the surface because the plasticizer comes from the book, goes to the surface, on the surface, they're going to be evaporated. When you have the renewal of the atmosphere, you are shifting the equilibrium to the plasticizer going out. If you do not have the renewal, then you have an equilibrium. Then the plasticizers on the surface might come back. It's a recent report showing that they could foster this comeback. So it's a good research achievement for art conservation. But so this renewal of the atmosphere and cold storage are the main strategies. Passive strategies, because you don't know nothing about the polymer. The conservation research is trying to be more active, so changing something in the polymer. And the problem is the composites. So imagine you have in the same piece something that release acids and must have the atmosphere renewed, and something that should not have the atmosphere renewed in the same piece. So we have a lot of composites. So you talked about computer. There is one art conservation working mainly on computer and robots, and there are dozens of different polymers inside. So it's a very complicated problem for conservators. And ID is a problem also. So they need to identify, and when you are an artist and you can state which kind of polymer you use it, it's okay. But when they receive the donation of some object and you don't have the information about that, they need to identify, and museums and art galleries suffer of not having the techniques to identify. This is one of the big problems. But the second question, you talked about what you could do as an artist, right?
I mean, it was more comment than a question, because I was just thinking if we should think about like this second life of our artwork, or even like dying of our artwork as a continuum of our process. So, okay, we are not going to preserve that. The museum is not going to invest money to find the best possible way, because from scratch, we can decide that, okay, our piece of art is going to exist in this like piece of device, but not forever. So
Yes.
this is also this traditional, let's say, way of thinking about art, which should be kept, and it should be preserved for next generations. But at the same time, everything, majority of artistic activities right now is ephemeral. So we should maybe transform our thinking that, okay, I am even open to see how my, I don't know, robot, my installation is dying with time. So that seems to be a really interesting concept for myself.
Yeah, I have a comment also. I have a doubt, actually. First, one comment regarding conservation. There are some conservators, as I mentioned before, saying that we shouldn't have so much efforts trying to preserve something that is going to just delay it, the decay. And second, there are some museums working with 3D printing. So they are building files so you can print the art in your home, or they could print it again when the 3D printing is degraded. So they create the art as a virtual piece, so you could reproduce when it's decayed. The second comment regarding ephemeral art, I have this doubt, because some ephemeral art are exposed in the environment, are exposed outdoor, right? If they are ephemeral, they are going to degrade. If they are degrading, they are going to pollute.
Oh yeah,
so I have this question, but also, if they are going to pollute, and I think this could be considered in the art, but also I don't know if we should stop doing that, because as a persons who have materials, we are polluting. When you walk with your clothes, you are polluting. This is a recent finding they shared yesterday. So I don't know if it's a thing, but I have this doubt how it can be deal with the pollution of the art in outdoor, but not saying that, oh, it's polluting. I think it's just another way to think. Okay, it's something outdoor. Some things outdoor are going to pollute.
It's interesting idea to think about art as about pollution in general.
So only conceptual art anymore.
I'd like to add something at this discussion, because we are here meeting in this Vara Cloud, Berlin, Tokyo, also in the way that we meet art and sciences meeting, and also this format of hybrid arts. And I see here, I think most of the artists here present, you would probably define yourself maybe very near working in the field of hybrid arts. And I think there I would like to maybe enlarge the art discussion today, Walter, and maybe also challenging a little bit the choice of your artistic examples, because I found them very representative. And this is maybe also my research I'm actually here defending, because working with found objects, objet trouvé, this is very modernist, and but putting them into painting or an image, this is very like what we would say in art theory, representationalism. And what I find really fascinating, and I'd like to actually roll over the ball to Nana, maybe if you want to contribute, or maybe I can say this about Nana. Nana and Kat, as two artists, but also like scientist artists, they realized microplastic workshops before last year and last year. And this is actually an artistic practice, working hand in hand with science. And I think the most fascinating point for me was it has a performative format. And it is not so much to construct an art piece as such, but to open up, to have an artistic practice that transports knowledge. And actually a lot of knowledge also that you gave us. And I'm very grateful that you gave this to us, and also much more from a specialist, a chemist point of view. But then also I would consider, please tell me, Nana, if I'm wrong, but what I really like to remember back from these microplastic workshops was the fact that we had a citizen science component. So here comes art and science, and we collected microplastics around the River Panke. And also Sarah with other workshops, you are also part of the discussion with microplastics. But I remember back, Nana and Kat, we built then all together a density column to exactly decipher what you were telling in the middle of your talk, if it's PPP or PPT, etc. And that was, I hope I don't exaggerate rhetorically, but I would say that had a magic power of a mixture of aesthetic, art, science, and knowledge gathering. On the basis of plastic gathering and collection. So I'd like to bring this into our discussion here, because I think this is, for me, this is 21st century art.
And actually, density one was quite wonderful because we were using honey, agave oils, cooking oil and water, like all these different, soap, and to measure out the different types of plastics that were found.
What would you say, Nana?
Yeah, I think. Thank you for this wonderful description, first of all, of this workshop. I also really remember back this moment of, like you're working hands-on on a project, or on a problem that you see maybe every day. You walk by the river and see it floating, and you've heard about microplastic before. And I think this process of going through it hands-on was really valuable for many pieces and for many people. And I come more from the science background. I think Kat had more experience on the artistic side, and together we were walking on this very thin line of these two fields crossing each other. And I think it's very, very valuable to generate knowledge and get people into contact, and also empowered to have a kind of, to feel empowered to have an opinion about it, to feel empowered to actually talk to other people about it, let's say. I have a comment to the discussion you had before with about conserving artworks or not. I think it's so interesting that also what you said, Walter, before, this like the divide between contamination versus pollution, that it's just a definition point actually. And it seems that we decide as humans when to preserve and when to not preserve. When do we want the polymer to be resistant and when not? If we use it in our buildings and technology, we want it to persist as long as possible. Same as with artworks, it seems we find it valuable to be passed on to other generations. But once we find it in nature, we rather want to get rid of it very fast. And I think this is something that we have to realize, that it's not going to be like this. I think we have more than, I don't have the number now, but we have crazy amount, like I think, was it 600 million metric tons of plastic ever produced? I forgot the correct number now, but it's out there in the ocean and in the soils everywhere. we won't get rid of it. I think this is an important thing. So it will be conserved, and it has also an afterlife. Like I'm working on microbial colonies and microbial lives that live in very close symbiosis with microplastic. And this is just one little part of zooming into what is happening around microplastic particles and what kind of biota is attached to it. This brings me to the artist from South Africa that you presented, that also got a new idea of, or like using plastic as a material, not just as waste, but giving it an afterlife. And I think it's a kind of tricky point of view to actually see also plastic as a potential, even though we call it contaminant, it still has potential for other lives, and other meanings. That's my comment to it. Yeah.
It's interesting because there are also there's clothing, there are objects that are made from plastic waste and are quite fashionable in a way, but then they of course, these also break down over time. It was also interesting, I was thinking about the art that's degrading and adding to microplastics, but I was also thinking in our workshops with bioart and hybrid arts, we have this interesting waste cycle. Okay, sometimes the one that we're told to pay most attention to is the bio waste, and some of it has to go to a laboratory to be taken care of, but others, sometimes it just goes in the organic waste because it's really just like old food. And then there's sometimes for an exhibition we might use glassware, but otherwise for a workshop we use what scientists mostly use, which is plastic. Plastic petri dishes, or the microscope, digital microscope use is made of plastic and will eventually end up in the waste at some point when it no longer functions. So there's this whole level of plastics that are involved just by taking over just by taking up over the scientific material, which actually kicks it back over to the scientific material, and the replacement of what would have been glass 50 years ago is now plastic almost all the time. Right?
Yeah, and I guess we all don't want to live in a medical system without plastics, for example. It's always very double.
Yeah, I think regarding this comment about thinking things lasting forever or being resistant to the time, or to the weather, or to stuff, so we can use. Today, we cannot live without plastics. If we replace plastics for other materials, we are going to be not wise, because to prepare something on metal or glasses, we spend more energy than plastic. So we are going to contribute to other problems. But I think we need to be wiser. Like in hospitals, we need plastics, we need disposable plastic, but we need to manage them better. Masks is going to be a hotspot. It's going to be an emergent pollutant right now. And regarding stuff lasting forever, it's one criteria before. We wanted this kind of materials because we should replace them less. But now we know that this is a bad criteria. We cannot produce things that last forever or that last longer, because they are hard to get rid of when they go to the environment. And one of the answers people are providing to the plastic pollutions now is circularity. So you can be wiser than before, thinking in stuff that's going to be circulated in our lives than in the linear production of materials or goods. But I also think that circularity is it's a good thing. It's better than before if we embrace circularity. But nobody's talking, when talking about circularity, nobody's talking about consume less, because circularity is not going to solve the problem. It's going to delay the problem. Because also when talk about circularity, it's not forever. It's not infinite. If you have recycling in the middle of your circular way to design your product and reuse your product, it's going to be degraded. And partially, some part of the circularity is going to the waste. It's impossible to have not waste, to not have waste. So I think we need to think about capitalism also. But that's, I don't know how to do it. Max Liberon does that much better than I just follow her. But I think this, and I end up knowing her because of the stuff on consumption. We need to deal with that. We need to approach that. And circularity can be understood as something that delayed the real discussion, which is about buying stuff, I think.
But how do you frame this? Well, there's a lot of new technologies, especially biotechnologies, that are now working on an easy digestion of, let's say, PET.
Yeah, the PET is people they have found the enzyme which breaks one of the bondings, which is the beginning of the process. They are not found the digestion of PET, but it's a good news. But it's sometimes you have the results in science and then goes to the media and the things get bigger than it is. But regarding that, it's good news. But which kind of good news is that? So we found a solution for a waste that shouldn't be there. So it's a solution for a problem we created. I think circularity, it has some advantage. Also green chemistry. Green chemistry, it's a field of chemistry which states about production. It's just about production of chemicals or products or goods or materials. And they state that things shouldn't last forever. They should be biodegradable. So I think regarding solutions we have to the current problems, they could be delaying of the real problem, which is having waste. So we find an enzyme to deal with the PET, but PET is going to the environment the same way. So we need to collect the PET from the environment and then process with the enzyme. It's the wrong discussion, I think. The PET shouldn't be in the environment first. And then circularity tries to approach that. And green chemistry also. So you must work with biodegradable. They should be integrated in the carbon cycle, in the nitrogen cycle, etc., to be allowed to have the risk to go to the environment. But all of this is expensive. So all of this, it's not affordable. We have solutions for the microplastics. It's not affordable. We cannot pay for that. So we need to find real solutions. And that's I don't know, there are some people from Berlin here. In Berlin, we have a museum called Futurium. It's a very nice museum. You go there, you have a nice time, you have fun. It's interesting to my daughter to know about technologies, but I personally, I don't like the museum. I like the museum, the space at the time I spent there. I don't like the approach because there they show all the solutions for the problems we have today. So we leave the museum thinking that, okay, it's good. We have the solutions. We have the technologies. So they don't show the technologies. They are making everything with fungi. So we don't need plastic anymore. But it's not scalable. Why we are not doing everything with fungi? So they are not showing the limits of the technologies. So when I think, I don't have the numbers, we need to go into the circularity, but when we go to the circularity fully, I think we are going to face that the problem is the amount of goods being processed and circulating all the time. I think we need to, I don't know how to do it, but I think the numbers are going to show us someday. I think shortly we need to have the real discussions. Sometimes I think we regarding sustainability, not here, but regarding sustainability, we need to talk about the real issues. And I think deeply is the consumerism.
Okay. Does anybody have any questions?
I would just ask a quick question. If you see a perspective of replacing plastic and artificial materials and using just fungi and different kind of ecological materials, because we are moving in that direction somehow. Getting to know about microplastic and how our earth is endangered. But yes, this is like ecology, it's like rational scientific thinking, and at the same time it's politic and economical issues. So yeah, I am just curious if you see the perspective in the future that at some moment maybe it will be not so expensive and it will be also more affordable in a sense.
Yeah, I think it's a futurology exercise, so it's hard, right? But yeah, technology advances. We have good ways to make production of alternative materials cheaper, and I want to believe that. But again, we are talking about everybody. So some scientists did the exercise of trying to wear everybody in the world with cotton clothes. We have no space to plant cotton for everybody. So we are not getting rid of polyester. Never, according to this calculation. So I think we can find. You were keen about the problem because we have the policy and the economy. Because if we are not reach the scale of the petrochemical industry, we will never know, or it's hard to know if we are going to be cheaper or not, because some process to make things cheaper must be in scale. So we are going to work that when we have scale. And consolidated industries, it's not just petrochemical industry. You go in the history of industry, you see sulfuric acid, which was the first acid produced to do stuff. So all production we have until 20th century were based in sulfuric acid, even if they could be based in other kind of acids. But it's a consolidated industry. It's expensive to change. It's the same. If you're going to change for biodegradables or other kind of materials, you need to get rid of a multi-billionaire industry in the world first. They are going to react. So they have lobbies, they have jobs, and it's right. Yeah, it's huge. You need to have them together in this. If you don't embrace the current technology, meaning if you go into breakthrough technology, it's a war. It's an economical war, right? It's hard. So I am not super optimistic because we have several startups. If you go to the startup ecosystems, you always find some startup working with fungi as a material. But I didn't find so far some startup becoming national or becoming a multinational company working with fungi. And they work very successfully with local products or local suppliers, local clients. So they do a lot of furnitures and they do very well, and it's a very successful company, but you don't see that nationally. So I would like to be optimistic, and I can't believe that we are going to have cheaper alternative and sustainable technologies, but it's harder than that. I don't know how to do it. I can't foresee a way to see that.
Yeah, it's a big political question in the end. As long as it's still cheaper to always produce freshly new polymers, it won't change. And I have the feeling that like I visited also several recycling companies and recycling landfills, and they actually all tell the same story, that it's just not profitable for them, even if they want to, because always recycled polymers are always still cheaper, not cheaper, but they get less money for it than if they not recycle. And it's a political issue. And I also have the feeling that now it somehow shifts, at least this is what I feel in our project, the momentum of the big plastic shock is kind of getting down in the public opinion, I feel. It seems like people are kind of okay with it, that the plastic is out there. We just need new technologies, new biodegradables, but there are very little projects working on how to get rid of the plastic that is already there, or what to do with the plastic in the environment. So I think it's a consisting problem somehow.
Yes.
Yeah.
Georg, how's the view from Japan on that, with artists or with culture?
Yeah, so I think the petase was mentioned. I think it was actually found in a Japanese recycling plant. Can you hear me actually?
Yeah.
You guys are a bit slow. Okay, great. So but it's very nice to hear that this is actually only the first part of breaking down the bed. I did not really know that. So thank you very much, Walter, for this very nice talk. I was also wondering about the labware, as Christian already mentioned, which is mostly polystyrene, right? It's BS, which is like styrofoam and the petri dishes. So I think this is quite an interesting dilemma, that labs have a huge output on plastic. The Japanese perspective. I don't know. Maybe what's unique here, there's a lot of that's maybe the trash sorting, the Müllsortierung is pretty famous here. So we have like, I think 24 different types of sorting the thing out. So I need to investigate this a bit, if it actually gets recycled or if it's more or if it gets burned. Yeah, but Walter, one technical question. You mentioned the plasma making is easy. So how easy is it to make this plasma into surface treatment? Because I would really love to do that.
I love this technology. It can be easy, but also can be tricky. I worked with plasma in low vacuum, so I should have it was super hard working to do that. But then I discovered room at room pressure plasma. So you have a pen. So plasma, in the slide, I didn't delve into the slide, but plasma, you produce a tension, a higher tension, when you have atmosphere. The tension is so high that you remove electrons. So you create, and you can do it in a way you don't have high temperatures. So you break everything is there. So if you do nothing, you break the air and you create reactive species, and you can break the surface you are applying, then you are removing the surface. It's one application. When you put into the process some chemicals, you can put other stuff, something with silicon, and then you break this stuff, you create very reactive chemicals, and then these chemicals bond chemically to the surface. And according to the chemical and to the conditions, you can create hydrophobic, you can create hydrophilic, you can create color, You can create, you can protect your piece of art from the oxygen, so the oxygen don't infiltrate in the plastic. So now with these pens, you can look for that and you can find, you have a like a luggage, a backpack with the engine, with the electronical part, and then the atmosphere you choose, and then you could work the surface. People use that in the dentist. You put a plasma in your teeth, so you create a surface so it's whiter. And you protect against the biofilms. It's completely, you can do it in your finger. It's super.
Yeah. Yeah, if you have some links, it would be really nice. I still cannot really quite imagine if it's suitable for DIY or not. Yeah.
I sent to Christian, and then
perfect. I'll send it around on the Facebook page. Okay, I think we're coming up on the 2 hours.
Walter, thank you so much for this
thank you.
wonderful insight.